Thank you, Miriam. Welcome to my talk, Inside Sensor Technology. My name is Thomas Metzger. I'm Technical Team Lead at the Sensors and Optics team here at IDS. Let's take a look at the agenda of my talk. Today, I want to tell you the general trends for CMOS image sensors and some causes for these trends. What hardware innovations for CMOS image sensors were made in the last years, and how the performance has improved with an example. Then we'll take a quick look into a general image pipeline. After this, with the pros and cons of several implementation concepts. And then, at the end, an outlook to smart features of sensors. Okay, let's start with the big common trend. If you think of the advertisements for smartphones and for their camera or other consumer cameras, there's often a sticker at the packaging that promoted HD, Full HD, or nowadays 4K or even 8K resolution for video recording. That's roughly over 30 megapixels. For snapshots, there are resolutions of up to 108 megapixels. A huge increase in the pixel count and driving promotional effects like with the gigahertz of computers some years ago. But the size constraints goes the other direction of even thinner and smaller devices. Thus, the size of each pixel is shrinking. Let's have a look at the trend of the pixel size. Here is a graph of the smallest pixel size in a commercial product over the year of the first use. Samsung is today in production with the smallest pixel of 0.64 nanometer for their flagship smartphone. OmniVision has announced a 0.61 nanometer pixel generation sensor for this year. The machine vision market is behind a bit, but already around 1 micrometer for rolling shutter and 2.5 micrometer for global shutter are in use for some sensors at a trend, and the trend is clear. But on the downside, smaller pixels means less imaging performance. With the same scene conditions in terms of less photons are hitting each pixel per time, just related to the available area for each pixel. The quantum efficiency, that's the probability a photon gets counted by the pixel, lowers. And the full well capacity, that's the maximum amount of countable photons for each pixel, each frame, reduces with the pixel size, and thus the peak signal-to-noise ratio over the sensor is shrinking. Also, other imaging parameters decreases, like the intrascene dynamic range. A more complex and expensive fab process with higher costs for smaller pixel structures need to be applied. So, why should smaller pixels be used due to the obvious less performance? Only for the advertisements? If we keep the target pixel count constant, like for a resolution of 4K image, and shrinking the pixels, that's an overall less manufacturing cost. Okay, I said before, a smaller pixel comes with a more complex and thus more expensive production process. But that's not all at the end. The keyword here is yield. So, what is yield? Manufacturers use wafers to produce tens or hundreds of sensors chips at one step. Those wafers are typically 8 or 12-inch wafers. For our example, here a 12-inch wafer is used with sensor sizes of 40 by 40 millimeters at the left down to 10 by 10 millimeters at the right. There is a typical random seed of defects across the wafer marked with small red dots. That will defects a complete sensor chip at that position. Those sensors are marked yellow in this example. The smaller the chips, the more can be fabricated with one step. That's simple. The defects will occupy less area to be wasted with smaller chips. Even at the end, a higher amount of chips are defect. The quotient of good chips to total chips manufactured is rising significantly. And that's the yield. For our example, lowering the chip area by a factor of 16 from left 40 by 40 mm to 10 by 10 mm at the right raises the amount of good chips by a factor of 62. The yield goes up from 35% to 94%. Now we can get back to our question, why at all make pixels smaller considering the lower performance? To conclude the effects of scaling, the chip production cost is highly correlated with the chip size. More chips per wafer means a higher yield. And the yield may outweigh the more complex manufacturing process for modern sensors. Also, there is a fixed offset to the total price when it comes to the testing, packaging and all that stuff behind, after the chips are separated from the wafer. Let's now take a look at what has been done the last years to improve the performance of the sensors and to compensate the lost size of each pixel. This is a simplified side view illustration of 3 pixels, each for a different color. We will focus on the optoelectrical performance and will skip in this talk the electrical evolution of 3T, 4T and shared transistor designs that also enable smaller pixels from the logic side due smaller occupied logic area. Also, we are looking just at the green pixel in the middle, only concerning the side effects to the neighbors. The incident light comes from the top at different angles. Looking closer to possible photon paths, there are a lot of photons blocked by the metal layers. Also, some of the light is passing through the filter, but will be catched by the wrong photodiode, dedicated to the red or blue color. The small e is indicating the position the photon is generating an electron-hole pair. The electron is moving to the doped area of the photodiode and the hole is drained by the ground substrate. For ease of use, we will just speak of electrons in the future talk. All red crosses are wasted or false positive photons. This is just simplified to better highlight the different issues. Now, what can be done to lower the blocking effect and reduce the crosstalk? There is a simple improvement to focus the light to the photodiode. A microlens for each pixel above the color filter array. This is a well-known technique today. Some sensors also have a double microlens to even better guide the light around the transistors and logic elements of the metal layer of a front-side illuminated sensor. When we take a look at some possible photon paths, you will see that the microlens will focus the light better to the photodiode. Less photons are blocked by the metal layer and less photons are catched by the wrong photodiode. A microlens improves the optical crosstalk. In terms of photons that will else reach the neighboring pixels, the quantum efficiency is enhanced as less photons are blocked and thus more photons will reach directly the photodiode. And the angular response is enhanced. This means photons from steep angles are better directed to the photodiode, especially for pixels out of the center of the image sensor. Some sensors also have optimized microlens positions according to the distance to the image sensor to adapt for steeper angles from small lenses like S-mount or lens modules. This will reduce the vignetting effect. That's shadows at the outer image area. But there are still some photons blocked at the metal layers. Can we get rid of those annoying metal layers for the readout circuitry in the light path? Yes, the metal layer position is flipped upside down and the light is coming from the back of previously the bottom of the sensor. This is called backside illumination or BSI. If we look at the light path of some photons, we see there is no more blocking of light at the metal layers. That's great. Thus, a lot of photons generate an electron for the pixels and the quantum efficiency raises. But there is still some crosstalk of photons and electrons reaching the neighboring pixels and generating false positives. Can the light and electrons be kept within each pixel? A structure like a wall can be built between the pixels. This is called deep trench isolation. There are several names for those walls describing the depth and the direction they are coming from. Either from the color filter side, that's backside deep trench isolation, or from the logic layer side, that's frontside deep trench isolation. This structure will keep the photons and the electrons within a pixel, thus reducing the optical and electrical crosstalk. It further enhances the quantum efficiency as the travel path of the photon is kept within the pixel. But there is still a little optical crosstalk from photons passing the green color filter and generating an electron in the red pixel. Also, no enhanced full wire capacity to previous concepts. Can this be done better? Now, with a better isolation between the pixels, the doped area can be enlarged. This is the storage of the photodiode. And thus, a higher full wire capacity can be reached to improve the signal-noise ratio and the intrascene dynamic range. For a better readout and better use of the large photodiode, the transfer gate is made in the vertical direction, here. As the photons are kept within the pixel, can this be utilized? Yes, after guiding the light through the color filter and focusing it to the pixel, and in the first thought, weird thing is made, here. The light gets scattered at the top. Thus, the most photons are not going straight through the pixel. This enlarges the travel path by bouncing between the deep trench isolation walls till the photon may reach the end of the pixel at the bottom. This technique is adopted from the solar cell technology. But what does an enlarged path within the pixel mean? Photons of different wavelengths means for the visible light the different colors do have different absorption depths. That means bluish light with short wavelengths have a high probability to generate right after short path within the pixel made of silicon already the countable electron. Light with a longer wavelength is absorbed with a lower probability, and thus longer travel path is needed to rise the detection probability. Look what will happen with the very long wavelengths of the near-infrared spectrum at the example later. And keep this technique in mind. There is quantum efficiency. The quantum efficiency is enhanced by factors. Can this early optical crosstalk from before be eliminated? The deep trench isolation cannot be made between the color filters, as they are kind of digged and refilled within the silicon. As the filters are made in a later step, on top, another additional structure is needed. Here, those are metal structures between the color filters to separate them from each other, also called buried color filter array, as the filters are embedded within a metal grid. This further reduces the optical crosstalk between the pixels. At the end, how far can we get? So, here's an example of two different sensors with the same pixel size. The left one is an older front-side illuminated pixel with microlenses already. The right one is a newer BSI sensor with no scattering surface. The boost in the quantum efficiency for green light is clearly visible, from 58% to 75%. Also, the saturation of the pixel, that's hand in hand with the full wire capacity, is increased. Thus, the derived parameters of the maximum signal-to-noise ratio is enhanced, and the intrascene dynamic range is enhanced. Improvements in the readout structures and analog-to-digital conversions of the sensor lowered the readout noise and contributed to the increase in dynamic range too. let's take a closer look at the quantum efficiency. This is the quantum efficiency, plotted by the light wavelength of an older frontside illuminated sensor with microlenses. One curve for each of the 3 different colored pixels of an image sensor with biopattern color filters. You see, the peak quantum efficiency of the green light is barely over 35%. Compared to the values before, this is not a good performance, but here the pixels are already smaller. Also, the quantum efficiency in the near-infrared wavelength is only a few percent. Let's take a look at a modern backside illuminated sensor with deep trench isolation and a scattered surface. Here, the peak quantum efficiency for green is over 80%. That's nice. And the near-infrared quantum efficiency is very high. If you compare both curves directly, the improvement is even more clear. This is an overlay of the previous curve. The lower curves are from the older sensor. There is a huge difference between the peak quantum efficiency at green and even more at the near-infrared. This improvements are made possible due to previously mentioned backside illumination, deep trench isolation, and the scattered surface for a longer absorption path within the pixel. But there's even more that can be done than pixel shrinking to shrink the size of the image sensor. Stacking wafers on top of each other. With stacking, a logic layer from a different wafer is put at the metal layer side of the BSI sensor. For the stacked chip, a different manufacturing process with a potentially smaller node size can be applied. Thus, more transistors and logic per area. The previously necessary logic of the ADC, the timing and the digital processing units placed around the active imaging array can be put in the additional logic chip below, and even more in terms of features on pixel levels or sensor level are possible. Thus, the sensor chip gets smaller and, remember, this lowers the production cost of the image array chip. Let's summarize the hardware aspects in short. Smaller pixel sizes means smaller sensor size with the same resolution. Smaller sensor chips means less production cost. A lot of hardware improvements are done to encounter the smaller pixel size. Large boosts are achieved in categories like the near-infrared quantum efficiency. Also, a wide field of opportunities for features is open with the chip stacking technology. And a newer and better sensor with the same resolution must not have higher production costs. Now, we have dealt the hardware topics and will continue with some software feature aspects. Here, we see a possible image pipeline from a camera and what processing steps could be done for a pre-processed image to correct different lens and sensor effects for good real-world reproduction. Some sensors offer such a pipeline or parts of the processing right at the sensor chip level. Thus, those processing blocks can be implemented at different locations, either at the sensor level as system on a chip or SoC, in a dedicated processing unit of the camera, the image signal processor or ISP, quite often a field programmable gate array, an FPGA, is used to be able to adopt the processing with programming, or even an implementation in the software at a host computer is possible. Processing images at the edge saves computing power at the host system. For a camera manufacturer, it may save development cost and time when there is no other ready-to-use image pipeline around, like an FPGA pipeline, and no need for an image signal processor. This means less hardware and thus less cost. Also, a smaller PCB footprint and a smaller camera can be built. If there are such benefits like the cost reduction, why is IDS still using an additional FPGA for the image pipeline? This is a good question only for those sensors that do support kind of a complete pipeline. We can have the same behavior for different sensors. Pipeline differences, like with the control interface or functionality mismatches between sensor manufacturers, we don't care about. It's all the same behavior with our own FPGA pipeline. Feature support across different sensors means also support across possible product follower within the same family. Don't be afraid, the machine vision products are very long-running products over several years. The features are adaptable for customer needs. The camera can handle the overall throughput better, like buffering with memory. The testing and evaluation with a known pipeline is done faster and more safe for an overall higher product quality. Also, there are way more performance feature options possible with an FPGA compared to on-chip solutions. Let's take a look at an easy sequencer feature. Many sensors do support some sort of image sequence, maybe for HDR or some different intrascene settings. This is an often available and simple sequence of 2 or 4 different exposure settings. But the core sequencing parameters are often limited to brightness control only. Also, the sequence path is straightforward with alternating settings every frame. Let's have a look at a possible camera sequence within an FPGA. There are more complex settings for each frame, like additional camera internal signals of input-outputs. Also, the path may be more complex and controlled within the camera and from input signals. This is a simple example why often FPGA implementations are of wider use, especially this is adaptable to customer needs. Also, the previous arguments for the image pipeline implementation at FPGA level are valid for feature implementations, like less effort for a new sensor for a camera family or higher product quality in terms of stability and testing. But beside all those benefits, it can be advantageous for the customer to even use a pipeline implementation at the host and do all the processing at the host system. This will enable even more flexibility for the customer, for example, to use a custom deburring or a totally custom sequencer. It will lower the manufacturing cost due to less chips and smaller and simpler PCBs. On the downside, this will increase the necessary computing power and thus also the necessary host performance. The cost of the host system, if not already oversized, will rise. And the performance of the complete imaging system may be limited not only by the interface bandwidth or sensor output. For the previous sequencing example, this will slow down the capturing of every single frame while reconfiguring the camera. But attention! Not every feature can be freely implemented anywhere. Look at this example image I took while skiing a few years ago. The display should show minus 18 degrees Celsius. For the human vision, it was all fine. But at the moment I tried to take a snapshot with my mobile phone, I got only several elements of the display each try. This is not the rolling shutter effect. This is called light flicker mitigation. The cause is a short integration time in combination with fast pulsing light elements. This is a man-made issue, and there are a lot of situations where this might lead to wrong evaluation results. There are special techniques at sensor level for light flicker mitigation. It's very hard to do the counteraction within a camera ISP or FPGA, or even a host system, due to a huge performance drop in the usable frame rate. The sensors will just do multiple even shorter exposure times within the previous same frame time and sum them up internally. I won't get into further technical details. This is just to keep in mind that depends on what you will do, you need to choose the matching performance of the camera system. To sum up this chapter over features and manufacturer design decisions, the overall performance and usability an ISP or FPGA solution is advantageous in various ways, like providing stable and well-tested pipeline features and capabilities to interact with the outside world. The system costs can be reduced with host implementations. The trade-off is the performance. System-on-a-chip features can be advantageous if they meet the needs. And not all feature concepts are of use. The necessary performance is mostly crucial, and a solution with an FPGA is favorable. Nearly finished. We will now have a look into trends of smart features that are even more to come with the capabilities of the previously mentioned chip stacking technology. Let's take a look at a previously used example with very boring content. We might take an image stream from this scene and we will see the flickering sign with the minus 18 degrees Celsius. But for this case, a lot of redundant static information is taken care of every single frame. I have roughly marked all the unnecessary content. Also, the most part of the display is static. Nice example for a region of interest, if you know where to look at and if the target is not moving. Could only changed information be transmitted by the camera or sensor? Yes, with event-based imaging. Every pixel can send an event when there is a brightness change. For our example, farthermost pixels will do nothing. In this example, at the top is a classic frame-based capturing. Below, the red and blue dots are events for higher and lower brightness of the pixels. The complete sky does not create events as there is no change within the capture time. A lot of logic is added for every pixel. This makes the sensitive pixel area very small and thus the size of the complete sensor huge and expensive. With chip stacking, the pixel sizes can be much smaller as the additional logic for the brightness evaluation can be put in the stacked layer. Thus, it is more compact and affordable. Another aspect is a high intra-scene dynamic range, as every pixel operates at the incoming brightness level, coupled with high-speed signaling. With event-based imaging, the scene altering contrast information is directly extracted at the edge, but still some host needs to get to use this information. The mighty Artificial Intelligence has also found its way into image sensors today. There are stacked sensors available with convolutional neuronal networks, called CNNs, to evaluate the image directly at the edge. They signal the outcome of this evaluation instead of some image data. We will not step into how those CNNs work or what they can be used for. This evaluation can also be done within the host with a high calculation effort or within a very performant implementation at a camera level. An implementation at sensor or camera level can reduce the overall system cost. A host computer used for the machine control is no more necessary. This can be done directly by the camera. If you want more information to the image evaluation with CNNs, you may check out our past and upcoming talks at the IDS Vision channel to our IDS Next camera. Now the conclusion in short. The sensor market has changed a lot and the technology is evolving. A good sensor does not make a good camera in the end. The complete system needs to fit. If there are special needs, just ask us. And we can deliver a fitting camera system for your needs. Thank you for your attention.